Okay, guys, welcome to the weekly contest 389. This is San. And today I'm gonna try to tackle the Q4 questions in the weekly contest. And as you can see here, I could not solve it in time. So obviously all these guys are you guys are just God. I don't know how you solve it. This is one of the gnarliest problem I have ever seen in LeetCode for a long time, so kudos to the person who actually come up with this question. I really enjoy it. I didn't solve it in time. I did have to spend some time to think about it a little bit afterward, but here we go. Minimum moves to pick K once. So let's just go through this problem a little bit. Right, we're given a binary array, nums of length n, and a positive integer k of non-negative integer max changes. Alice plays. Okay, so they changed it to Alice. It used to be Dylan, who is so Dylan Smith was one of the person who performs really well. So they have a traditions of using the name of the contestant for the problem description, but apparently he complains about the name actually distracts him a little bit, so they changed it back to Alice. But okay, so the goal is for Alice to pick up K once from nums using minimum number of moves, right? When the game starts, Alice can pick any index, called Alice index, in the range of 0 to n-1 and stands there. If it is a 1, she picks it up and it becomes a 0, which does not count as a move. This is a really confusing part, but once you kind of reframe the problem a little bit, then it kind of makes sense. I'll get into that later. After this, Alice can make any number of moves, including 0, where in each move, Alice must perform exactly one of the following actions. So she can select any index that is not her standing location, so not Alice index, right? Such that nums j and set numj's equals to 1, meaning that like she can put a coin. You can think of it as like put a coin in a location that is not hers. This action can be performed at most max changes time. So you can kind of think of it as like in max changes time you can put a coin. Now select two, the other action is select two adjacent indices x, y, right? Such that one of them is 1 and the other is 0, and then swap the value. If I equals Alice indices, then Alice can pick up after the move, and nums y becomes 0. So this sounds really confusing, but you can think of it as like she's kind of sucking the coin into her locations, right? So we can kind of go quickly into an example here. So let's assume that Alice is here, right? So first of all, she will pick up this coin 6, right? So we no longer have this coin 6 anymore, right? And then here she can do two things. One is that she can put a coin somewhere, right? So this is the first move that she can put. So that's very easy to understand. She cannot put it here. She has to pick it in the location that is not at her standing locations. And then the other action she can take is that like she can pick any adjacent number in which there's like one coin and no coin, and then kind of swap around. So you can kind of think of it as like she just kind of moved the coin, right? And she has to pick up K coins. So in a way you can kind of think of it as like the second move just means that she's just kind of suck one of the coin nearby to her locations, right? There's no reason to really suck away from her because you would have to suck it back to get K. So this is really just like just like sucking the coin. Now let's talk about this max change things a little bit, right? The only implication of this max changes is just that like you can kind of reduce the problem of picking K's a little bit by doing this thing. That is, you literally just put a coin that is like right next to you, right? And then just suck it in. That's it. You can just sort of keep doing it and keep doing it. So you can think of max changes as a way to reduce K. Mostly that's a more correct way to understand it. And then it is sort of always advantageous for you to do that most of the time. because like most of the time the coins are really far away, right? So instead of kind of sucking coins toward you, like why don't we just kind of put the coin right here and then suck it, and then put the coin and then suck it, and take it, right? So you can think of max changes here as a way to reduce the problem as much as possible. Now, it is not always advantageous to actually use the max change all the time. For example, as a simple example here, right? Let's say k equals 1. Let's say k equals 1, right? Now, and then max change is also equals 1. You can either put a coin here and then suck it, which is 2 moves, or you can just suck this coin indirectly, which is just 1 move. So it's not always advantageous to use like max change up to maximum, but in general, it is a pretty good thing to do. And in general, like whenever you don't want to do max change, there's only 3 cases you want to do it, which is when you already standing in the location where there's a lot of coins nearby you that you don't want to, that you don't have to put it in anymore. Once you are kind of like 2 places apart, right? Once you're kind of like 2 places apart, for example, like here, for example, then it's kind of always advantageous for you to put coin, because it will take 2 moves to suck this coin in, and then it's also take 2 moves to put this coin and suck it in. So really, there are like, you should always use max changes to put coins, and then the minimum that you can go down to is max change minus 3, especially like the only amount where you don't want to use up to max change is max change minus 3, where you're standing right there and kind of like suck these 3 coins in, right? So yeah, that's the first thing. That's the first thing that you have to do. The second thing is that, like, okay, once you use up all these max changes, right, then it is really just a matter of kind of picking the A locations where the total amount of distance from A to the K coins surrounding it is the smallest possible. For example, let's assume that max change equals 0 here, and k equals 4, right? So if k equals 4, then because you cannot put the coins anymore, you have to stand somewhere and then you have to suck the coins in, and that would take like 1 move, 2 move, 3 move, 4 move, 5 move, 6 move. You get the idea. Essentially, you get the distance from A to all the K coins surrounding it, right? And I think the challenges here is to actually do this very efficiently. How do you find the minimum distance to K nearest coins in a very efficient manner? And this is and the solution to this is actually a very gnarly sliding window. So again, let's assume that k equals 4, right? And if we use a sliding window, the first thing to do is that you actually append the positions of the coins here into a separate array. So you can see that I kind of already do it here for us. So because these are the coin positions, so I add 1, 4, 3, 6, 4, 5, 6, 9, 11, and 12 here. And then because k equals 4, you kind of look every window of 4 here. So 1 to 6, 4 to 9, 5 to 11, and then 6 to 12. Right. And then for each of them, you have to find the distance. You have to find like the minimum locations to put in. And part of the thing about sliding window is that you always have to think about a way to calculate the value of each window very efficiently, ideally over 1. And that is a very difficult part. And you have to recognize 2 things here. First of all, you should recognize that for every k, for every window of k, is always the most advantageous to put A in like the middle coin. Either middle coin is actually fine, but it's always advantageous to put it in the middle coin, because you can kind of think about it this way. Let's assume that these are 4 coins, right? Every time you go from here to the left, from this location, the distance from this one is increased by 1, but the distance from the other 3 decreased by 3, right? And then it just keep going, and then just keep going up to here. But now, from this point onward, every point that you increase adds to 2, but then you also reduce the distance from the 2 other coins to 2, right? So you can think of the total distance as sort of like just keep reducing until you are in the middle of the 2 middle coins, where the total distance is equal, and then going up again. So it's very important to recognize that you should always put your coin in the middle of the 2 here. And once you recognize that that you should put in this coin, the second thing that you need to do is how to do this kind of distance calculation. This distance calculation efficiently. So here you will need to understand this trick called sum so far. So the distance from all the left coin to this coin is the sum of these value, right? The sum of these is the sum of these value. You calculate the sum of these value first, and then you take this minus the number of left coins, multiply by the this position multiplied by the number of left coin minus the sum of all the numbers from the left side. Maybe it's actually better if I do like multiple coins here. You need to take the sum of positions of these 2 coins, and then you take this multiplied by 2 and then minus that. And then for any coins on the right side is the reverse. You take the sum of this and then you minus this, multiply by 2. And then to get the sum of these, you can do like a sum so far. You can do the sum so far. So let me actually go with this little example. Actually, so let's assume that you are dealing with this part of the array, right? You put your middle coin here. Let's calculate the sum so far. So sum so far is 0, 1, 5. So 1 plus 4, right? So sum up to this point is 5, 9, and then this is what 15, right? Let's assume that your location is like 4, right? So now there's one coin on the left. So the left side, the total distance will equals to 4 times 1 minus sum so far up to 1, so 1 minus 0. And this would be 3, right? So exactly 3. There's 3 distance here. Now the sum on the right side would be the sum of like the total sum of this array, which is sum so far of this point minus sum so far of this point, right? So that would be 15 minus 5, which is 10. So 15 minus 5, which is 10, minus this position times 2. So 4 times 2 here. And that means that the total distance would be oh, my bad. I think I make a little bit of an error. So this has to be 10, and it has to be 16, right? Yeah. Let me kind of change that. So this should be 10, and this should be 16, right? Because 5 plus 5 is 10. So the sum of all the number up to this point is 10, no, is 16. So if you want to calculate the sum of these small range, you take the sum up to here minus the sum up to here, and that would be 16 minus 5 minus 4 times 2. So that would be 11 minus 8 equals 3. And yeah, 3 is the correct total distance, because it's 1 distance from this point and 2 distance from this point. So it's 1 plus 2 equals 3. So I'm just showing an example here to show that you actually need this sum so far trick to be able to calculate the total distance very efficiently. It is going to be an O of 1 to decide the coin in the middle, and it's like 2 operation, which is also O of 1 to calculate the distance from k nearest coins to there. And then because you check every single array of k consecutive coins, it will be an O of n minus k operations for this. Now, because we do max changes minus 3, and we don't always want to use all of the max change as I have shown, right? So what we need to do is that we have to try max change minus 1, max change minus 2, and max change minus 3. So because there are like 4 cases of them, we simply need to just try for every single cases. So 4 times O n minus k, which is still like O of still just kind of O of basically just an O of n if k is very small. And obviously you need like an O of n to create this like sum so far array. So if you do all of this very gnarly stuff, then the algorithm is just an O of n. It's just an O of n algorithm. And then by checking every single window and every single combinations of max changes, then you would basically just find like the smallest number of moves there. Then you just should just return it, and that would be the answer. I did say a lot there, so let's actually just go through the actual code itself here. So first of all, this is the creations of the array that I mentioned before. This is the sum so far array from the positions, and then here max change is equal min of max change times k. So this is just a simple trick. So like you really don't need like too many max changes. Like if you need like less k coins than the max changes, then you don't really need to put in too many coins in, right? So max change can be fine here as is. And then this is where the sliding window algorithm happen. You have something called mean coins changes. So this is the change that you decided to use from the max changes. So that is the input. Notice, so after you do the change, which is the trick of putting the coins and pick up right away, then you have the rems, which is the remaining, right? If the remaining is 0, then that just means that your total move, if changes times 2, which is the put in and then suck in, and put in and suck in, put in and suck in, so change times 2. Else, you kind of have to set it as like a base number of move. Maybe this is not a really nice way to go with it. Like maybe this is a better piece of code to write here. But anyway, if you have nothing remaining, then just return that number of move. But if there are still some coins remaining, then you have to do the sliding window tricks, right? And here's the sliding window, very gnarly stuff right here. First of all, I create something called the side coins. So side coin is like the number of coins either on the left or on the right. And then this is the middle coin. So middle coin, I is the beginning of the ranges, right? And then middle coin is just I plus the number of side coins, which is the middle coins. So here I have the before cost and after cost. Before cost, as I mentioned, is L. L is the position, so L mid times side coins minus this is where the sum so far stuff comes in. Here, this is the total sum of positions of the coins on the left, and once again for the after, this is the total coins from the right, minus this remaining number of coins. And then you have the total, which is the base plus before plus after, and then this is the return value. So we are trying to find the min here, so you only just want the return to be as small as possible in where you return. Now, as I mentioned, we don't always need to use all the max changes. So we do want to try from max change -3 to max changes. So basically rerun the algorithm 4 times and then find the min and then find the return. And then let's try to submit it and see if we got it right. So yeah, very gnarly stuff. I think this problem, if you consider all the issues related to it, then it's actually pretty simple. But during the crunch time and with this very lengthy description, it was really hard to see the problem with clarity. So I was really struggling to do it properly. But hey, congratulations to the people who were able to solve it, and looking forward to the next competition. Good luck to you all for implementing this algorithm. Cheers.